In the early morning hours of August 17, 1933, on the Baltic coast of Germany, a small group of engineers gathered around a narrow launch stand at the Kummersdorf Proving Grounds. The air was still, the horizon pale, and a single experimental rocket, coded A1, waited for ignition. When the engine fired, it rose briefly from the stand before tipping violently and crashing to the ground. It was a failure, but it marked the true beginning of a program that would, over the next 3 decades, evolve into the very foundation of the American space effort. The men behind that early attempt were led by a remarkable 21-year-old engineer named Wernher von Braun. His assignment from the German Army was starkly simple: develop a large, liquid-fueled rocket capable of reaching supersonic speeds. The pursuit of this particular technology was dictated by the harsh geopolitical realities stemming from the restrictions of the Treaty of Versailles, which had severely barred the development and deployment of long-range artillery. Rocketry offered a critical loophole. It was not explicitly banned under the treaty's terms, and it offered a potential means of delivering military payloads at distances previously considered impossible. By 1934, after a necessary series of failures and crashes, the team began the grueling process of understanding the fundamental challenges of liquid-fueled flight. Each crash and aborted test answered specific, expensive technical questions. Why did those early rockets spin uncontrollably almost immediately after launch? The answer lay in previously undetected faults in gyroscopic stabilization. Why did engines explode on ignition, consuming the delicate motor structure? This was traced to uneven fuel flow and dangerous combustion instability. Why did the structures themselves collapse under maximum thrust? The root cause was identified as inadequate metallurgy failing under rapid heating. Every single technical failure was meticulously recorded and analyzed, and each result decisively shaped the next design iteration. On December 20, 1934, at Kummersdorf, the A2 rocket achieved a flight to an altitude of approximately 2,200 meters. This measured success convinced the German Army High Command that larger, sustained investments were absolutely justified. The team's growing ambitions required substantially more space, expanded fuel storage capacity, and significantly longer testing ranges. Consequently, in May 1937, they relocated their entire operation to a remote island on the Baltic, Peenemünde. This location was strategically chosen for its isolation, its flat terrain, and its direct access to the sea for downrange testing without endangering civilian areas. Construction moved with impressive speed. By mid-1938, Peenemünde was a sprawling industrial complex consisting of specialized test stands, massive assembly halls, advanced wind tunnels, precision machine shops, and what was recognized as one of the most advanced measurement laboratories in all of Europe. Engineers now focused their collective energy on a new, far more demanding objective, the A4 rocket, which would later become universally known as the V2. The ultimate technical goal was to build a vehicle capable of delivering a 1-ton warhead over 300 kilometers, reaching the very edge of space along its ballistic trajectory. The technical problems encountered were truly unprecedented in engineering history. To maintain control, engineers had to determine exactly how a vehicle behaved when passing through both transonic and supersonic regimes, leading to the construction of specialized wind tunnels capable of testing models at speeds exceeding Mach 4. They developed complex turbopumps capable of injecting alcohol fuel and liquid oxygen into the motor at rates exceeding 120 liters per second. They were forced to test entirely new alloys to withstand the horrific combustion chamber temperatures of over 2,500 degrees Celsius. By March 1940, the first A4 prototypes reached partial thrust on the massive Test Stand 7. Failures, though expected, continued to plague the process: engine burn-throughs, structural buckling, and guidance malfunctions. But following the established iterative methodology, each failure was converted into a technical cause and effect. Uneven cooling channels were identified as the reason a combustion chamber cracked during the ascent. Magnetic interference within the guidance compartment caused critical gyroscopes to drift. Pressure surges during rapid throttling were the cause of fuel line ruptures. In March 1942, the team prepared for the first full-scale launch attempt. On June 13th, the rocket rose briefly, lost control, and plummeted to the Baltic. An inspection quickly identified a failure in the control vanes. A second attempt, on August 16th, achieved 11 seconds of flight. On October 3, 1942, at 15:58 hours, Peenemünde finally recorded a complete successful flight. The A4 ascended 84 kilometers into the stratosphere, traveled 190 kilometers, and impacted the sea. With this single launch, it became the first man-made object to reach the fringes of space. With proof of concept established, the German leadership ordered mass production. In late 1943, following the bombing of Peenemünde, manufacturing was transferred to underground tunnels at the Mittelwerk complex near Nordhausen. Labor for this massive industrial task was supplied by prisoners from the adjacent Mittelbau Dora camp. Conditions in the tunnels were harsh, and mortality rates were high. From a technical standpoint, the speed and secrecy of underground production resulted in a cost-to-quality control, with engineers frequently reporting structural defects, wiring errors, and fuel tank inconsistencies in the finished rockets. By September 1944, the first operational V-2 rockets were fired at London from mobile launch units. The rocket traveled at nearly Mach 4 and could not be intercepted. Despite this speed and range, the V-2 suffered from significant accuracy limitations. Engineers analyzing the launches documented that minor gyroscope errors, inconsistent fuel mixtures, vibration during launch, and atmospheric variations all contributed to guidance drift. By March 1945, more than 3,000 V-2 rockets had been launched. For the engineers at Peenemünde, the military value of the rocket was limited. Its greatest significance lay in the technical achievement it represented. It was the world's first long-range ballistic missile, first guided supersonic weapon, and the first human-made object to travel into the upper atmosphere. As Germany collapsed in April 1945, the rocket teams faced a profound decision. They could surrender to Soviet forces advancing from the east or to American forces from the west. The Soviet Union already controlled the Peenemünde site, capturing equipment and some remaining personnel. But the core engineering group, a vital cohort of around 120 specialists, chose to move south toward Bavaria. They carried with them not only their persons but also critical assets, documents, blueprints, and key components. On May 2, 1945, they formally surrendered to U.S. forces near Oberammergau. The United States immediately initiated Operation Paperclip, a classified intelligence operation designed to extract this scientific expertise from the defeated enemy. The engineers were meticulously interrogated, screened, and transported to the United States between September 1945 and early 1946. Their initial destination was Fort Bliss, Texas, and the White Sands Proving Ground in New Mexico. Here, the German team's first assignment was to reconstruct the very V-2 rockets they had designed and fired, using captured parts and components that were shipped en masse from Europe. This reconstruction and launch program was less about demonstrating wartime capability and more about rigorous scientific inquiry. Between 1946 and 1952, the engineers launched more than 60 V-2s at White Sands. This test series was a dedicated effort to study the upper atmosphere, cosmic radiation, and, crucially, to convert the German program's internal knowledge into quantifiable, empirically verified data essential for future American designs. Each launch answered specific research questions that built directly upon the failures documented at Peenemünde. For instance, the tests provided the first comprehensive data on aerodynamic heating during re-entry.
Engineers analyzed why fins had previously overheated and determined the precise role of plasma formation and the necessity of greater heat shielding. They also studied the complex fuel behavior during ascent. They conclusively determined that cavitation, the formation of vapor bubbles in low-pressure liquid oxygen feed lines, was the cause of turbopumps seizing during ascent. Furthermore, they established that trajectory drift was often caused by gyro drift, exacerbated by prolonged storage. These tests formed the indispensable technical basis for all subsequent American missile development. The German experience had provided the initial concept. The White Sands testing provided the empirical data and diagnostic methodology. The structural load analysis techniques developed for V2 fins were now standardized, and the performance curves for alcohol-oxygen engines refined through this test series guided the design of America's first-generation boosters. The knowledge of how gyroscope drift increased with temperature fluctuations recorded in earlier logs was formalized here, setting the stage for future guidance precision. In 1950, the Army transferred the German team to the Redstone Arsenal in Huntsville, Alabama, to begin the highly focused work on a new generation of reliable, long-range missiles. The goal was clearly defined: to produce advanced, powerful, and reliable systems using every lesson learned from the decades of testing, the original A4 failures, the White Sands data, and the accumulated knowledge of material science. The contracts that followed were written in language cold enough to mask their scale: procurement of liquid fuel rocket engines, test support equipment, range instrumentation, engineering services. Each line was a small doorway into a technology the United States had never attempted at this scale. In Huntsville, the Army let von Braun operate with striking independence. The understanding was simple: build rockets that could hit targets an ocean away, and do it faster than any adversary. The ethics of importing knowledge born in a forced labor cavern went unspoken, subsumed by strategic necessity. Von Braun's team approached the task with the same industrial methodology they had refined during the V2 program. They began with the engine, mapping out the specifics of combustion instability. They identified the absolute operational limits of turbopump speed. They defined the tolerances not as ideals, but as consequences dictated by the laws of physics. Every single component, the injector plate, the regeneratively cooled chamber, the high-pressure piping, was cataloged, diagrammed, prototyped, destroyed, and rebuilt. Where American engineers suggested safer, more conservative pressures, the German specialists insisted on pushing the operating envelope higher. Where the Army questioned the need for so many test firings, von Braun reminded them that data, not optimism, created reliability. Their initial major output appeared in 1951, the Redstone missile, deployed in August 1953. It was not merely a copy of the V2, but the first American ballistic missile built under a vertically integrated workflow, a groundbreaking system where materials procurement, precision machining, assembly, propulsion testing, and vehicle integration were all concentrated within a single industrial ecosystem. The Redstone's engine produced more thrust, its guidance was substantially more stable, and its overall reliability was measurably higher than its ancestor. Its design directly applied the knowledge transferred from the V2 program. It had a range of 320 kilometers, used alcohol liquid oxygen propulsion, but crucially featured a more advanced inertial guidance system. Engineers had incorporated the V2's documented drift coefficients as baseline values when designing the improved systems, following the methodology of measuring bias, applying correction functions, and validating with range tracking. But engineering never exists in a vacuum. Every advance demanded a corresponding advance in infrastructure. Huntsville's industrial landscape began to transform rapidly. Machine shops expanded exponentially to accommodate new, stronger alloys. Test stands grew taller and were structurally redesigned to safely restrain engines approaching the physical limits of metallurgy. Supply chains rerouted to feed a program that consumed stainless steel, copper, specialized wiring, telemetry equipment, and computing power at an unprecedented rate. Entire neighborhoods were built to house the massive influx of workers, American engineers, technicians, machinists, and welders, who now collaborated daily with the German team. What had begun as a wartime intelligence operation had rapidly become an American manufacturing engine. The next assignment pushed the team even harder. The United States demanded an intermediate-range ballistic missile with significantly greater range than the Redstone. The answer became Jupiter. To achieve the necessary performance, the team was forced to reinvent the fuel system, dramatically increase the tank volume, redesign the structural load paths, and completely re-engineer the combustion cycle. Each modification solved one problem, while inevitably exposing three more. The pervasive issue of combustion instability, a constant threat since the days of Kummersdorf, again threatened to tear the engine apart within milliseconds. Vibration harmonics forced unexpected redesigns in the airframe. Guidance precision had to increase beyond anything the team had previously attempted. The Army demanded timelines the physics struggled to respect. Yet the result, after hundreds of tests, revisions, and failures, was a missile capable of delivering a payload across thousands of kilometers with dependable accuracy. It was not elegant, but it worked. Output replaced rhetoric. Data replaced speculation. A clear pattern re-emerged in the newly consolidated American aerospace industry. When von Braun's group was given a technical objective, they produced a solution, complex, industrial, iterative, and empirically validated. Meanwhile, the geopolitical context shifted dramatically under their feet.
In 1957, the geopolitical context shifted under the engineers' feet with stunning finality. The Soviet Union launched Sputnik 1 on October 4. Its beeping radio signal crossed the night sky and instantly transformed global calculations. For the first time, the United States experienced the industrial shock of being definitively technologically outpaced in a critical new domain, orbital flight. The Army, already working closely with von Braun, understood that the critical infrastructure and the expertise required to launch a rapid response already existed in Huntsville, waiting only for authorization. The team had a launch-ready vehicle, the Jupiter C, capable of orbiting a small satellite. Bureaucratic hesitation had previously delayed its deployment for scientific purposes, but the launch of Sputnik removed that hesitation entirely. On January 31, 1958, the United States successfully placed Explorer 1 into orbit. The rocket that carried it bore the unmistakable structural design derived from the Redstone, with an engine heritage reaching back to the Mittelwerk design and systems integration guided by the Peenemünde engineering methodology. But its successful launch marked a conceptual break from that origin. For the first time, the team's immense, cumulative engineering work was formally directed toward exploration and scientific inquiry, rather than exclusively toward military targeting and war. The consequences for the organization were immediate and profound. The U.S. government established the National Aeronautics and Space Administration, or NASA, on July 29, 1958. The Army Ballistic Missile Agency transferred its space-related personnel and activities to this new civilian organization. Huntsville's Redstone Arsenal became the geographical and intellectual center of America's massive push into space. Von Braun was named director of the newly formed Marshall Space Flight Center. The German team, once scattered across military bases, was now consolidated into a single, unified scientific institution under civilian oversight. Their next technical task dwarfed everything that had come before it. NASA demanded a booster powerful enough to lift humanity and its complex hardware beyond Earth, a program that would become the Saturn series. No existing engine, no existing fuel system, no existing test stand, and certainly no existing manufacturing facility could meet the unprecedented specifications. The project therefore demanded the immediate construction of an entirely new, colossal industrial landscape. The Mississippi Test Facility for full-thrust, sustained engine firings, the Michoud assembly facility for fabricating the giant tank stages, and the towering vertical assembly building at Cape Canaveral for stacking a vehicle taller than a skyscraper. The design began with abstract numbers, millions of pounds of thrust, hundreds of thousands of kilograms of propellant, and structural loads distributed across complex multiple engine clusters. But those numbers translated instantly into real physical problems that had to be solved at scale: intense thermal stress, unpredictable vibration frequencies, and acoustic pressure levels capable of damaging delicate instrumentation. The necessary solutions required engineering at the absolute edge of available material science. Welders had to develop novel techniques for fabricating thin-gauge metal tanks capable of holding super-cold cryogenic propellants. Turbopumps had to be engineered to withstand rotational forces magnitudes higher than anything in the Jupiter or Redstone rockets. Fuel mixtures had to be optimized for maximum specific impulse without compromising combustion stability. As the rocket architecture took shape, the Saturn I validated the critical clustered engine method. Engineers studied why large engine clusters produced low-frequency oscillations. The cause was identified as combustion instability, resolved by applying the refined methodology used in the earlier missile programs, resulting in baffles, injector redesign, and pressure feedback systems. The Saturn I-B increased thrust and proved that the guidance systems could handle the unique dynamic demands of crewed flight. But the ultimate objective remained: the five-stage behemoth, the Saturn V. Development began in 1962. Its first stage utilized 5 F1 engines, each producing 1.5 million pounds of thrust. The engineers confronted a series of unprecedented challenges. They addressed the decades-old issue of gyroscope precision by designing the Apollo guidance platform to be insulated and temperature-controlled, thereby maintaining stability within tenths of a degree, a level of precision that built directly on the V2 and Redstone drift analysis. To maximize performance, the use of cryogenic propellants, liquid hydrogen, in the upper stages was necessary, requiring the development of highly insulated tanks to limit boil-off. The most critical dynamic challenge was mitigating longitudinal oscillations known as pogo, caused by acoustic feedback between thrust fluctuations and the rocket's flexible structure. The team solved this by inserting a helium-pressurized accumulator into the fuel line, a complex engineered dampening system. The F1 engine's injector plate went through dozens of configurations after early tests revealed chamber-destroying combustion instability. Engineers introduced specialized baffles in the injector face, modifying spray patterns until combustion stabilized, a sophisticated application of the same fundamental diagnostic logic first attempted in Peenemünde. Testing began long before assembly. Engines were fired repeatedly at full power, their exhaust tearing into sound suppression systems built specifically to survive the violence. Stages were shaken, stressed, frozen, heated, and shaken again. Instrumentation recorded thousands of variables to ensure that no unknowns remained. For the team, failure data was never a setback, it was critical information, and the engineers consumed that information as fuel for the next design iteration. When the first Saturn V rolled out of the assembly building, its scale seemed almost implausible. It stood taller than the Statue of Liberty, supported by thousands of welds, miles of wiring, and the output of dozens of factories across the country. It represented not a single achievement, but a network of industrial victories: material science, propulsion, guidance, manufacturing, quality control. And every one of those victories had roots that could be traced back through Huntsville, through Fort Bliss, through Peenemünde, back to the moment when the United States absorbed a defeated enemy's engineering brain trust. The launch of Apollo 8 in December 1968, the first crewed mission to leave Earth orbit, marked a critical turning point. Saturn V performed flawlessly. For the first time in history, humans saw the far side of the moon with their own eyes. The technology that made it possible had been shaped by decades of iterative development, by thousands of workers, by decisions that had blended scientific ambition with geopolitics and moral compromise. But the ultimate test arrived on July 16, 1969. As the Saturn V ignition sequence began,
5 F1 engines roared with a combined force unmatched by any machine before it. The rocket lifted from the pad not with grace, but with determination, forcing its way upward through controlled chaos. Every vibration, every fluctuation in pressure, every deviation in thrust was monitored by systems designed using principles first articulated in German research papers from the 1930s, refined through American industrial capability in the 1950s, and validated through relentless testing in the 1960s. The mission that followed, Apollo 11, completed a trajectory that had started in a war-ravaged laboratory on the Baltic Sea.
The mission that placed humans on the moon did not erase the need for continuous engineering work. After Apollo 11, the Saturn V continued in service for several missions, with each launch providing crucial additional engineering data. The vibration records from the Apollo 12 launch, for instance, confirmed that lightning strikes during ascent caused transient electrical disturbances, but did not compromise the guidance platform because of its built-in internal redundancy. The Apollo 13 mission in April 1970, although a near disaster, yielded valuable insights into structural resilience after the service module explosion. Engineers studied why certain components remained intact despite rapid depressurization, and this analysis contributed directly to later improvements in spacecraft safety procedures and materials selection. The final Saturn V launch occurred on May 14, 1973, carrying Skylab into orbit. The vehicle's upper stages had been modified to accommodate the station's massive size and unique shape, requiring engineers to reinforce structural sections based on load predictions derived directly from earlier flights. The knowledge developed across 3 decades, from A4 test stands in the Baltic to the Saturn assembly buildings in Florida, had successfully culminated in a launch system capable of placing the largest payloads in history into orbit. Throughout the 1970s, NASA strategically shifted focus from heavy-lift, expendable vehicles toward reusable spacecraft. The Space Shuttle program adopted and expanded many core principles developed during earlier ballistic missile research. Studies of aerodynamic heating during atmospheric re-entry, a field of inquiry initiated with the earliest V2 launches and rigorously extended through the Mercury and Gemini programs, directly influenced the design of the shuttle's complex thermal protection system. Engineers analyzed why re-entry heating peaked at certain altitudes and how different tile materials responded to extreme plasma conditions. Shuttle orbiter development relied on sophisticated methodologies for structural stress analysis that had originated in wartime Germany and were adapted and meticulously expanded through decades of American engineering work. The long-term impact of the German engineers extended deeply into propulsion research as well. The fundamental liquid oxygen kerosene propulsion cycle that powered the V2 later resurfaced as the power source for many subsequent American designs. Testing data and analytical methods from the Redstone and Jupiter programs guided research into stable combustion, injection dynamics, and turbopump efficiency for new propellant types. Although NASA increasingly developed its domestic engineering expertise, the foundational physical principles established in the 1940s remained consistent and foundational. By the late 1980s, the generation of engineers directly involved in the wartime rocket program had largely retired. Their immense contributions, however, remained permanently embedded in the physical and intellectual infrastructure of American aerospace. Documentation, technical papers, performance charts, and test logs meticulously preserved the evolutionary path of rocketry from its earliest stages. Each subsequent milestone, whether in missile development, satellite launch, or human spaceflight, rested on this vast cumulative body of knowledge. The facilities themselves reflected this unwavering evolutionary line. The architectural principles used to design the concrete foundations and flame trenches in the 1940s at Peenemünde were replicated and scaled up in the test stands at White Sands and later at Huntsville and Stennis. Engineers calculated flame temperatures, exhaust velocities, and structural heat loads to determine concrete thickness and reinforcement requirements. Test stand design became a precise discipline guided by decades-old data. The tracking networks expanded similarly. The early radar systems used to follow V2 launches provided the first understanding of how to monitor high-speed objects over long distances, techniques that American engineers used to build global tracking networks for satellites and lunar missions. The underlying progression from early German rockets to American space exploration follows a direct technical path defined by relentless problem-solving and empirical data. The trajectory from Peenemünde to Apollo was rooted in technical necessity. Germany pursued rockets to bypass treaty restrictions and to develop long-range capabilities. The United States adopted the technology to advance its scientific, military, and strategic objectives. At every stage, engineers addressed the same specific questions: how to stabilize a rocket in flight, how to manage fuel flow at high pressures, how to withstand structural loads during ascent, and how to guide a vehicle across hundreds of kilometers with precision. The entire path was defined by continuous experimentation, rigorous failure analysis, and incremental refinement. V2 test flights provided the initial measurements of aerodynamic heating. White Sands launches produced data on turbo pump behavior and trajectory dispersion. Redstone tests yielded insights into rocket staging and guidance accuracy. Saturn development introduced new materials and structural designs capable of lifting multi-stage vehicles into space. By the 2000s, the influence of the early rocket programs remained profoundly embedded in modern aerospace. Liquid engines continued to operate using principles established in the mid-20th century. Guidance algorithms still relied on inertial measurement units refined through decades of incremental improvement. Structural engineering continued to apply stress analysis methods consistent with those first used to evaluate thin-walled rocket fuselages. Aerodynamic studies still relied on shockwave behavior first observed during early supersonic tests. Every major achievement in American spaceflight had a direct technical lineage that extended backward through time, confirming that the continuity of engineering knowledge formed the ultimate backbone of rocket development.